Get that recorded, we'll begin. Okay, so I got the notification that it's recording. So before we get started on the presentation today, I just wanted to put a few comments out there for you guys over the weekend. So the first thing is that as of today, you should be able to access the combustion lecture quiz or the reading quiz. So do take a try at that. You do get 2 attempts. So make sure that you work through that. It's related to both combustion, more of the energy balances, and then also the adiabatic flame temperature, which is what we're going to be covering today in lecture. So just a reminder, that is due, I think Monday, or I think it was the day it's due, but make sure you just go ahead and take a look at that, answer the questions. I think there's a total of 4 questions to be answered. Next thing to note is next week in lab, we are going to be having the exam. So do make sure you start studying over the weekend. There's some extra example problems to kind of work through. So if you want to do that on Monday or Tuesday before the exam, take a look at those. And then the last thing to note is your homework will be due on Monday. It's related for all of the combustion, so make sure that you started it early. Try and get through most of the homework. Like I said, you might not be able to quite finish up the adiabatic flame temperature until Monday evening, but I want you to have everything else. Try and get everything else done as early as possible, because if you wait till the last minute, that homework set will seem like it takes forever just because there is a lot going on in combustion. So start early, try and get that done. Okay, so those are the general comments that I had. Otherwise, let's go ahead and start talking about some of the common terms that we have for combustion, and then get into this last topic, which is probably the most tedious topic in all of thermo. And that is going to be our adiabatic flame temperature. Okay, so the first thing I wanted to do was, now that we've kind of talked about the mathematics behind combustion, is introduce some of the common terminology that we have for combustion. And so looking back at some of the things that we've done, we've now taken our fuel and our air and we mix them together and we got our products coming out. And so whenever we did this reaction, we were going to be able to look at what the difference in the enthalpy coming in. So this would be the enthalpy of the reactants. Over here, we'll have the enthalpy of the products. It should be a product, not reactant. And so we'll be able to figure out the difference between these two, and that will give us some sort of energy that would be released. Now, generally, we would say this is going to be heat transfer or heat transfer rate out. Now, in terms of any time we have a reaction going on, if we wanted to look at the difference in this enthalpy, but yet we fixed the state, so we had the air coming in and the fuel coming in, we'll call this the reactant state, so we'll have some sort of temperature and pressure on the reaction side. And if we end up having the same temperature on the product side, so we have the temperature of the reactant, temperature, or the pressure of the product reactant here, sorry. If we have that same state at the inlet and the outlet, we can look at the difference between these two enthalpies, and we can call that the enthalpy of reaction. And so the enthalpy of reaction is basically just anytime we have a chemical reaction now, we can see what the difference is in the enthalpy at the standard state or just a given state, and we can use that to figure out how much energy is going to be released for a given reaction. And so usually that represents like the maximum amount of energy, because that represents the same starting point and ending point in terms of thermostates. And so generally that is kind of an upper limit. We usually won't ever get that amount of usable energy out. And so that is what we refer to as the enthalpy of reaction. Now, it can be used, and I want to point this out, to find the enthalpy of formation. So if we know what the common substances coming in, so oxygen, nitrogen, are generally what we bring in with the air. What we leave, we have carbon dioxide, water, oxygen, and nitrogen coming out. And so if we know all of the thermodynamic properties of that, if we wanted to then calculate what the enthalpy of the formation of the fuel was, well, if we use this method, we get everything coming in at the same state, everything going out the same state, and we measure what the enthalpy or the energy that was released during that process, we can then get the enthalpy of formation for a unknown fuel using the enthalpy of reaction. So enthalpy of reaction is not the same as the enthalpy of formation, but it can be used to help find the enthalpy of formation for an unknown substance. Now, if we wanted to then go ahead and talk about what is the enthalpy of combustion, well, first let me write out the enthalpy of reaction here. This would be the enthalpy of the products minus the enthalpy of the reactants. And so we would be getting out some energy if we do this, which I think I may flip that. But basically we have the difference between those two that will give us the enthalpy of reaction. We can then say, well, the enthalpy of reaction is going to be the enthalpy of combustion if we go through a combustion process. So if we put fuel and air together, we combust it. That will now give us the enthalpy that will be released for this given setup. And so these two are going to be the same. Just slightly different nomenclature because it's now combustion rather than just a general reaction. So basically the same interchangeable for what we want to look at. Now, the next ones are going to be related to how we can interpret this. So we have what we refer to as now the heating value, or it's going to be the amount of energy that's going to be released during the reaction, particularly a combustion reaction. And we do this when the products are going to be returned to the same state as the reactant. So basically we said, okay, if it's going to get returned to the same state, the heating value that we have, this is just going to equal, and we'll have to make sure to put the absolute value of the enthalpy of combustion. And so the heating value is, again, just related to the maximum amount of energy that we're going to be getting out for any given reaction, because we have to have the same state between the inlet and the outlet. So we'll note that this also has to include the products. So when we have things enter and leave at the same state, that will be the maximum amount of energy we can get out. And so the heating value generally represents the maximum amount of energy that we'd ever conceivably be able to get from a fuel. Traditionally, we'll get less energy out than what the rated heating value is, just because there may be some losses and we won't be able to utilize everything in a perfect kind of world, if you want to think of it like that. And we'll talk a little bit about that on Monday of what actually happens and how is this kind of modeling that we've done kind of an idealized setup. But basically, this is the theoretical maximum we could get for the given setup. Okay, and so when we do talk about the heating value, there are some additional terms that we usually break down. And so those are going to be referred to as the higher heating value and the lower heating value. Now, in terms of the higher heating value, we refer to this as we get more energy out of the combustion process because we are going to let the water that is in the product be in the liquid form. And so when we have the liquid, we have the enthalpy of the reaction plus the enthalpy enthalpy change as we change it from a vapor to a liquid. And so we're going to get extra energy from the phase change of water. And so this is going to represent the most amount of energy that we could have. So if we went through a combustion process, we bring it all the way back down to the same state as our inlet condition. And then we also get the water that's in the system to condense. We'll get more heat out of our system. And so that gives us the highest energy content that we could get. So that's what we refer to as a higher heating value. And then the opposite would be the lower heating value, where the water and the products stay in the vapor form. And so the difference between these two is going to be related to the phase change of the water, or the enthalpy of vaporization, which is HFG from the tables. And so that will vary what the difference is in our combustion products. Now, for most cases, unless you're bringing it back down to very close to room temperature or very cool, most of the time, if you think about when combustion is going to be leaving a system, it's generally going to have the gases are going to be heated up. And so generally we'll see in terms of the product value, the lower heating values are generally going to be what we see in gases. But again, you can take this into account. There's going to be different approaches. And so if you ever hear about the higher heating lower value or the lower heating value, that is the nomenclature between them. Now, in terms of a nice little figure here, if we bring in fuel, we bring in air, we go through the combustion process, and we get the products out in the vapor state. This is going to represent the lower heating value. We will have basically the lower heating value equaling the regular amount of heat out. If we want to now adjust that for the higher heating value, we just, again, scale it with the mass of H2O and then the enthalpy of vaporization, and we can move between those two if we, say, assumed a lower heating value, and we then wanted to calculate what would be the maximum heating value that we could get for the system. Okay, so those are some of the basic terms I wanted you to be aware of. So if you do spend some more time with combustion, at least you can kind of understand some of the nomenclature that we have. But at this point, I want to go ahead and shift gears and start talking about the last of our main kind of homework style problems and homework style questions, and that is going to be regards to the adiabatic flame temperature. Now, this topic is probably one of the most tedious and time-consuming problem sets or problem setups that you can have in applied thermo. So we'll let you guys know that ahead of time, but we still need to cover it. We need to talk about what it is and what does it mean and how do we actually implement the kind of a problem-solving strategy to complete this. And so in terms of the adiabatic flame temperature, we see in the very beginning here, we have adiabatic. We remembered from thermo. 1, adiabatic means heat transfer goes to 0. And so what that means is all of the energy that we bring in the fuel and in the air has to remain in the fluid. And so while we could go through this combustion reaction, we generate no heat out. And all of that has to now leave the system with the products. And so if we think of it kind of simply, instead of releasing heat to be used elsewhere, the combustion reaction is designed just to heat up basically the fluid element, and all of that energy has to stay in the flow. And so we're heating up the flow into the maximum potential. And so the adiabatic flame temperature, it just means that our combustion process is now going to occur adiabatically, and all the energy has to now be staying in the flow of the system and leave in the products. And so this is what we mean by the flame temperature now, is the flame temperature is meaning that when all of that energy is absorbed into the product stream, we are going to be able to see that it will be the maximum temperature that we could expect our gases to leave the system. So flame temperature in this regard means that we are looking at what is the maximum temperature of the fluid. And so this will be, if we had this combustion process happen perfectly, we didn't lose any heat, what is the maximum temperature that we will ever see? And so that would be useful to know if you're designing something that you have to know what you're designing it to contain combustion. You want to know what is the maximum value that it could be designed for. You're going to take a look at the adiabatic flame temperature. So to be able to figure out what this flame temperature is, we're going to have to do an energy balance. And so starting with conservation of energy, we're going to be able to assume that it's operating at steady state. And so we have then our heat transfer terms, plus we'll do work in just to switch it up today. And so we'll let the work in and heat transfer values go to 0 because we're assuming that it's adiabatic. And so what we're left with is now we have the sum of all of the flow rates in, so that'll be all of our reactants, times the enthalpy of that state, minus now the enthalpy of the reference state, plus now the enthalpy of formation, minus now the sum of all of the products that are going to be leaving the system, the enthalpy at that state, minus the reference enthalpy, plus now the enthalpy of formation. And so we see that this is just our general energy balance. But now what we see is if we quickly rewrite this, well, we're going to have the sum of all of the flow rates on the product side times the enthalpy of the state minus the enthalpy of the reference state plus the enthalpy of formation. This has to equal the sum of all the flow rates on the reactant side, enthalpy of the state, should be minus now the enthalpy of the reference state plus the enthalpy of formation. And so what we said before, all the energy that gets brought in with the fuel and the air has to leave now in the product state. And so it just comes down to balancing out all of these enthalpies and figuring out how do we account for all the energy. And the short answer of this is now we're trying to solve for what we refer to as the adiabatic flame temperature, maximum temperature. This maximum temperature will be the temperature of the products leaving the system. And so this is what we're trying to solve in this equation, which means we have to have an unknown in this equation. And so if we're trying to solve now for the temperature of the products, temperature of the products will be over here. We'll assume that we can measure what is the temperature of the reactant coming in. So usually standard temperature, pressure given for those. And so that means we would be able to know the reactant side enthalpy. We'd be able to know our reference temperature and the enthalpy of formation. Those are set. But on the product side, we can measure we know what the standard reference state is. We know what the enthalpy of formations are. But what we don't know is this enthalpy that we have at the state. So let's go ahead and put this in. So what we need to do is we need to now figure out what is this enthalpy here, because this enthalpy, if we remember, is going to be just a function of the temperature of the products. The temperature of the products is the flame temperature. And so what we're going to do is we're going to solve for that final temperature by solving for this final enthalpy, which means that we have to do a little bit of work to get this to come out. Now, to make this all happen, we have to rearrange this because we know that this enthalpy is not just of one point, it's of all of the flows coming in. And so on the flows coming in, we had oxygen, we have nitrogen, and we have our fuel coming in for the system. We have then the products going out, we have carbon dioxide, we have water, we have nitrogen, we have oxygen. And so we had to do this balance across all of those different species. And since we're looking for the product side, we have to figure out what is the enthalpy now related across 4 different substances. And so that's where the trick of this, or the complication of this comes down to, is making sure that we can account for now solving for 4 enthalpies simultaneously. And so if we wanted to write this out just so it looks nice, let's go ahead and do that. So again, we have to solve for this enthalpy, but the way that we have to do this is we have to still consider that we have to do this on the product basis. So again, solving for this, we now have the enthalpy at the state. This value means that we're just separating this part that we know out, and so we can move the enthalpy of the referent and this enthalpy of formation over to the other side of the equation. And so the form that we're going to end up using looks like something like this. We'll have the sum of all the flow rates of the reactants coming into the system. We'll have the enthalpy at the inlet state minus the reference state plus now the enthalpy of formation. And then now we're going to flip this to the other side. And so we'll have minus the sum of the flow rates on the product side. But we're only going to do this because we've separated this term out into its individual components. And so what we'll have is the enthalpy of the formation minus the enthalpy of the reference state. And so by doing this split, we said everything that we now know, because we'll know the inlet state, we'll know the enthalpy of the references, we'll know the enthalpies of formation, is now put on the right-hand side of the equation. So the right-hand side, so I'll call this right-hand side, is going to be a value we can just go ahead and put into our calculator and calculate. But the challenge comes in on this left-hand side, and we'll do this a little bit in red, because now we had to sum over 4 different species. So we'll have CO2, we'll have H2O, we'll have nitrogen, and we'll have oxygen. And we have to figure out a common value for their enthalpies that will give us one set temperature. Because remember, all of these are set for a temperature. And so we now have to figure out how to solve this system to actually be able to narrow down what that actual value will be. And so this left-hand side basically is going to represent our unknown. And so to actually be able to solve this unknown for the temperature, so we need to solve for T of the product side. Well, the short answer is this becomes an iterative solution. Which means that we have to guess a temperature look it up, look up all of those values of enthalpy in the textbook, see if that's close, and just keep repeating that over and over and over again until we find a value that works pretty good. Now, if we didn't have complete, so the question here is if we didn't have complete combustion, yes, you'd have more unknown enthalpy, so you'd have to include everything else. And so when we do the adiabatic flame calculation, we have to assume that we have complete combustion. Now, if we didn't have complete combustion, it's definitely not going to reach the same level because we're not going to get the same energy released. One of the biggest releases of energy in the system is actually going to be related to the formation of carbon dioxide from carbon monoxide. And so we won't see that we won't maximize the temperature output of the product. And so in this case, yeah, we'll have to assume that we have the complete combustion for this process to proceed. But that's a good question. Okay, so in terms of the solution, we know that it's going to have to be an iterative setup. And so the real question that we have to ask ourselves is, where do we even begin? Because we don't want to set ourselves up for a lot of work. We want to have a pretty good estimate to where to start. And so for the iterative solution, we want to start with all products. So start by assuming all products are going to be nitrogen. And so if we make the assumption all products are nitrogen, well, why does this help us? Well, if we think back to the examples we worked, when we did that, when we did like our mole fractions, our mass fractions, we found that like on the mass basis, it was like 75% or more of the mass that goes through our system is just in nitrogen. And he said, well, if nitrogen is going to dominate by mass, how about we just say take it from 75%, assume that it's 100%. That should give us a reasonable estimate of what's going to happen, and then we can adjust from there. So just making that assumption, it will get us in the ballpark that we want to do. And so the solution that we're going to start with for this is, we'll make a note, is substitute in now, we'll sum over all of the products on the mole basis, but we'll just assume that the enthalpy can be modeled as nitrogen. And so what we see is if we do the sum, we'll get sum of n dot of all of the products. But instead of using the individual enthalpies, we will just assume that they all have the enthalpy of nitrogen at this given value. And then we said, well, this is going to equal the right-hand side. The right-hand side is just this value that's up here. I just didn't feel like rewriting this entire portion. So right-hand side just comes down. We could calculate all of that. And so what we now do is we solve for HN2. And once we can find that value, because now everything was just related to the number of moles, then we take this value, we do a table lookup. If I can spell today, table lookup, and then we do some linear interpolation to figure out what the temperature of the product is. Now, tying this back to the iterative solution, temperature of the product, we then say, well, this would be the first assumption. Now, the first assumption here will always be an overestimate. And so whenever we want to start iterating, we're going to drop the temperature down a little bit before we start. And so my note on why this happens is if we go to the textbook lookups, and I'm not going to actually show this, but if you were to do this, you'd find that the molar version of enthalpy here is always going to be lower than the values for water and carbon dioxide. So the molar enthalpies for H2O and CO2 will always be much greater than the values for nitrogen. And so when we made the simplification assumption that our products were all nitrogen, well, we underestimated the enthalpies of the CO2 and water components. Even though there's not as large as the enthalpy by mass fraction, these energies do come into play. And so that makes this estimate always be on the high side. And so whenever you want to try and now iterate, I would say your first guessed value should be about 100 to 150 to 200 Kelvin lower as a starting point, just because add lower here, just because of the fact that your first guess will always be the overestimate. And so once you have your first guess, you reduce the temperature, you now put your temperature in over here, and then you iterate until you actually get the correct solution. And so, like I said, this does take a little bit of time, and it takes a little bit of practice. It's probably one of the more tedious setups that you can do in at least thermodynamics here. And so at this point, I wanted to go ahead and show how do we actually put this into a problem and run the numbers before we get too far. And we'll come back to the concluding remarks on Monday's class when we kind of wrap things up. But at this point, let's go ahead and try and get a little bit done on this example problem for the adiabatic flame temperature. So let's get started here. And on this problem, we are going to be working on our octane gas. We've seen this one before, so we'll be able to set up our stoichiometric balances. We're going to be burning it at, it's going to come in at 25 degrees Celsius. We're going to be burning it with 30% excess air, 1 atmosphere, and we've decided to throw in a curveball and say that the air is now moist air. It's got 60% relative humidity coming in. So we have to make an adjustment there, but we're asked to calculate what is the adiabatic exit temperature of the product gases. The adiabatic exit temperature will be our adiabatic flame temperature. So that's the maximum temperature that we'd expect given the given setup in terms of the combustion exit. And so let's go ahead and start this problem first by writing down all of our knowns and then progress through the problem. And like I had mentioned, I think early in class, we probably will have to finish this up on Monday. So wherever we get to at the end of class is where we will pick up in class on Monday. So the first thing that we have as far as a known is that we're going to be dealing with C8H18, which is just our octane gas. And we have the inlet temperature coming in. This is going to be 25 degrees Celsius. We said this temperature will go to 298 Kelvin, and we'll note that this is going to be the same as the reference temperature. Our other known features is that we have the amount of excess air equaling 30%, which means 130% theoretical air, which means that our stoichiometric multiplication value will equal 1.3. And then the last thing that we'll have to deal with is that we have a relative humidity coming in, and that is going to be 60%. And so we'll have to now alter our combustion reactions to take into account the humidity levels. And so let's go ahead and say now that we have what we know we're going to be looking for, and in this case we are looking for the product temperature, and this is going to be the adiabatic flame temperature. I can spell adiabatic today. And so that is what we're going to be looking for. We have to now get from our knowns to the find statement, and we are going to have to do that by making a few assumptions. And so in terms of our assumptions, we're going to assume that this is going to be defined by an open system. We can operate in steady state. And that all of the components can be treated as an ideal gas. And that the ideal gases that we have variable specific heat. And so just to kind of show what we're doing, we basically have the same kind of combustion chamber that we've been kind of looking at. And so it's just the open flow. We have the products leaving, and we have our two flow streams coming in. We're going to have the fuel flow stream, which is our octane gas, and then we're going to have our air coming in, and we'll make a note that this is going to be moist air in terms of our actual system, which means we have humid air coming in. And so once we've gotten the problem set up, we can begin our analysis. Okay, so where do we want to begin and how do we want to approach this problem? Well, we're going to begin the analysis the same way that we've begun most of our combustion problems. We're going to do the stoichiometric balance for our very simple combustion, our perfect combustion analysis. And so in terms of perfect combustion, we now have C8H18, our octane gas coming in. We are then going to bring in, and to start things off, we want to assume that we have it perfect, which means we have dry air coming in, and we're doing this for the perfectly stoichiometric balance, 3.67 and 2 coming in. And this is just going to give us the amount of water that we'll have form, plus then we'll have some CO2 form, plus, just to simplify this, 3.67 times A times N2 leaving the system. So this represents the simplest form of the stoichiometric balance. And so going through and doing the individual element balance, we'll see that if we deal with carbon, so well, we've done this balance before, so we have 8 carbon on the left-hand side. We have C number of CO2 molecules, so 8 is going to equal C. Doing now the hydrogen balance, we have 18 hydrogen on the left-hand side in our fuel. We're going to have B number of hydrogen on the right-hand side, but we have to multiply that by 2. And so we end up having B equaling 9 because we had 2 hydrogen in our oxygen molecule. And so we can then go ahead and proceed, or I should say not oxygen, in our water molecule there. So we can then proceed now onto oxygen, if I can spell. And so in terms of our oxygen molecule, well, we had 2 oxygen molecules on the left-hand side. So 2A, this is going to equal now on the right-hand side, we have 1 in the water. So we'll have B plus, we'll now have 2 in the carbon dioxide. So 2C. And if we go ahead and do this balance, what we find is A is going to equal 12.5, and we've seen that in our previous examples. So that is the simple stoichiometric balance, but now what we have to do is we have to adjust this. And so in terms of adjusting the stoichiometric balance, we're going to say we now have X equaling 1.3. We now are also going to have to take into account a relative humidity equaling 60%. And what does the relative humidity equaling 60% have to or mean in terms of this system? Well, simply put, what this means is we are going to have water in the vapor form in the reactants. And so we have to now alter our setup for the problem. And so if we go ahead and redo this, what we get is we'll have C8H18. We then have to adjust the amount of air molecules we have being brought in. So we have the A times X, O2 plus the 3.76 times N2. Now we're going to have a new variable D for the water vapor that is being brought in. This then combusts, and it's going to give us the variable over here. Now I'm going to go ahead and combine some things, knowing that I could do this in the balance form, but we'll have A plus D of H2O plus then CO2 plus then the 3.76 times A times X times N2 plus then we have A X minus 1 for our O2. Now, what I went ahead and I did in this setup is when I did the balances, when we add H2O, yes, we're going to have some more oxygen that we need to account for. We're also going to have some more hydrogen, but the only way our balance will actually end up working out is if we get the hydrogen to balance. And the way that we'd have to balance that is to get all of the hydrogen going into the oxygen here. And so by doing just the hydrogen and carbon balances, we end up seeing that this value becomes just B plus D. And so I left out that little bit of an exercise showing how it ends up working out. It ends up being that we just have B plus D now for the number of hydrogen molecule, or not hydrogen, water molecules in our system. We can just proceed with that assumption. And so what this allows us to do is we can say once we've done that balance and that setup, we know that we're going to have 1 kmol of fluid or fuel molecule coming in. A times X, we solve for A in the first part, 12.5. We now have multiplied by 1.3. This becomes 16.25 for the A times X. We then can go ahead and calculate, well, we don't know this value yet. We don't know this value yet, but we said, well, in the terms of our balance, we know the C coefficient here, that's going to be 8. Well, we'll note we do know B. B was 9. We can say, well, we can calculate the A times X times the 3.76. This will equal 61.1 kmol of N2. And then we know that AX minus 1, this is going to be the 3.75 for the number of moles of oxygen in our product. Okay, so now that we've done all of that, we need to now figure out what is the value for D. And so we need to solve for D to figure out what is this new variable that we have in the stoichiometric balance. And so to be able to figure out, I should say 4 here. So to solve for this value, we have to use what we know to figure that out. Now what we know is going to take us a few steps back, and we're going to have to go back into our humidity chapter, some psychometrics, and we're actually going to take it one step further. We're going to go all the way back to gas mixtures. And so starting though with what we know, we were given that we have a relative humidity of 60%. And so that is phi equaling 60%. And if we go back to the psychometrics chapter, we said relative humidity, this would be the partial pressure of H2O divided by the saturation pressure of water at the given temperature. And so at this point, we said we know the temperature. We can look up P sub G. And so doing that in our back of our textbook at 25 degrees Celsius leads to the partial pressure of the gas at the saturation conditions being 3.1698 kilopascal. And so once we know that value, we can now say, well, the only thing we could now work for is the pressure, partial pressure of the water vapor. So this would be our phi times now P sub G, which is our saturation condition. And since we know 2 of the 3, we can calculate the partial pressure of the water vapor. Partial pressure of the water vapor will be 1.9019 kilopascal. And so we now have some partial pressure of the water, but we have no idea where to go from here because we were able to calculate that from our known setup, but we just don't know what that piece of information gives us. And so this is where we can say, well, we used our terminology from psychometrics. We got one thing down. Let's go ahead and take one step further back, and let's go back to the gas mixtures chapter. Now in the gas mixtures chapter, we said, well, if we had a partial pressure, we could relate that to our mole fraction. We could relate that to YH2O. And so if we said we now want to figure out what is the mole fraction of water vapor, well, mole fraction when we did all of our laws of partial pressures for an ideal gas. So that would be pH2O divided by our total pressure. Okay, so at this point we know pH2O, we just calculated that. So what is the total pressure? Well, if we scroll back up here, we have that we're going to be dealing with everything at 1 atmosphere. So 1 atmosphere, this would be 101.325 kilopascal. And so at this point, if we wanted to, we could just go ahead and calculate the mole fraction. But what would we do with the mole fraction? Well, the short answer is the value of the mole fraction doesn't tell us anything in and of itself. But what it would allow us to do is it would allow us to now figure out the number of moles that we would have in the system. And so rather than just solving for this value directly, we can say, well, the mole fraction by a definition is the number of moles of H2O that we'd have on the reactant side divided by the total number of moles on the reactant side. So note that that is on the reactants. And he said, well, that is great, but how does that help us? Well, let's go ahead and expand this out. And so in terms of the number of moles of H2O, this would be H2O. We're looking for this value. On the reactant side, well, for the air coming in, we have to note this is just of the air coming in. We would have the oxygen, we'll have nitrogen, and we'll have water. And so this would be the number of moles of oxygen plus now the number of moles of nitrogen plus now the number of moles of H2O that we all had coming in on the reactant side. Because again, this is before we've added the fuel because the fuel is in a separate line. And so we now just need to be able to do this calculation. And we said, well, do we know any of the number of moles for O2, N2, or H2O? And said, well, we're probably going to have to look for the number of moles of H2O because that's what we don't know. But do we know anything about O2 or N2 that could help us? The short answer is if we go back up to the stoichiometric balance, we're doing this for 1 kmol of fuel. And you said, well, if we're going to do this for 1 kmol of fuel, we can say substitute in that NO2 would equal A times X. And so A times X is just the amount of oxygen coming in. And so that is going to be 16.25 kmol. And if we do the same thing for nitrogen, so this would be N2, well, that's going to be 3.76 AX. And so if we do that, we should get something like 61.1 kmol of nitrogen coming in. And so if we now know nitrogen and oxygen moles, we can solve for the number of moles of H2O. We'll note the number of moles of H2O, if we solve it in this fashion, will just equal the stoichiometric coefficient. And so at this point, we know our pressure, we know our other pressure, we know all of these moles. We just have to solve for the number of moles of H2O. And so separating these out, we have NH2O. In terms of the process, we'd first have to separate this out. So 1 minus pH2O, which is our partial pressure, divided by the total pressure. This would equal the number of moles of oxygen plus the number of moles of nitrogen times then the partial pressure of H2O divided by the total pressure. And then going ahead and now solving for NH2O, which we'll note is the coefficient D. This is going to equal, and I'm going to try and give myself some room here, the number of moles of oxygen plus the number of moles, should be N, number of moles of nitrogen, times now the partial pressure of H2O divided by the total pressure of the combined system coming in. And all of this is now going to be over 1 minus the partial pressure of H2O divided by the total pressure. Okay. And so once we do the setup, we realize everything now is known. And so the number of moles of H2O, which is equal to the stoichiometric coefficient of D, will equal 1.48 kmol. And so after all of that work, we come back up, we plug in 1.48 in for our coefficient of D, which makes this combined parameter over here 9 plus 1.48, so 10.48 kmol over here. Okay. So now that we've gotten through the initial stoichiometric kind of setup of the problem, we now want to push forward into the actual adiabatic flame temperature, and that has to be done through conservation of energy. And so writing out our conservation of energy equation, we have dE dt. This is going to be equal to Q dot in minus W dot out. We can assume the left-hand side goes to 0. We've assumed adiabatic. We've assumed there's no work. And so what we're left with is now the sum of all of the molar flow rates of the reactants coming in times now the enthalpy of the state minus the enthalpy of the reference point plus then the enthalpy of formation. And then this is done on the reactant side. And so we can then subtract off the number of moles on the product side, the enthalpy of the product side, so H minus H ref, plus now the enthalpy of formation. Okay, and so what we see here is we can get the same setup where we had in the slide. The sum of all of the products has to now equal the sum of all of the reactant enthalpies. And so what I'm going to do is I'm going to go ahead and write this out. And this is going to probably be the last thing that we get. And we may be able to simplify it a little bit. But we're going to try and set ourselves up so we have the reactant side equaling the product side. So basically what we're doing is we're just going to set these two equal to each other. And so let's start on the product side. And so on the product side, we are going to have our 4 main flows coming out. So we're going to have the flow rate of water, and we'll note this is going to be on the product side. We'll have the enthalpy of the water at the state minus the enthalpy of the reference point plus the enthalpy of formation, and all of these on the molar basis for H2O. We then are going to have the molar flow rate now for, what's the next one? CO2. And so we'll do CO2. And then we'll have the enthalpy minus the enthalpy of the reference state plus the enthalpy of formation for CO2. Then plus we'll have N dot of nitrogen on the product side. We then have the enthalpy minus the enthalpy of the reference state. If I can spell reference here, reference minus the enthalpy of formation. This is all for nitrogen. Plus then we have the molar flow rate of oxygen on the product side, enthalpy minus the reference enthalpy plus the enthalpy of formation of oxygen on the product side. And so all of this is now going to have to equal, and I'm going to just go ahead and bring this over. So because I'm going to run out of room, so this is equal, I'll indent it maybe a little bit here. All of the flows on the reactant side. And so on the reactant side, we have the fuel coming in, C8H18, and we'll have an enthalpy at that state minus the enthalpy of the reference state, plus then the enthalpy of formation of our C8H18. Then we have plus the flow rate of oxygen coming in on the reactant side. And so this will be the enthalpy of the state minus the enthalpy of the reference point, plus now the enthalpy of formation, all for oxygen. Plus now we have the flow rate of nitrogen on the reactant side, the enthalpy minus the enthalpy at the reference state, plus the enthalpy of formation. And then lastly, we have plus the flow rate of water on the reactant side, the enthalpy minus the enthalpy of the reference state plus the enthalpy of formation. And so this is why this problem is probably one of the most tedious setups, because of the sheer number of lookups that we need to do. Now, I do know that we're really close on time, so the last thing that I want to do was just to cross out some of the things that we know can go away. And so what we know is that the inlet state, our reactant side, the enthalpy at the state will be the same as the reference. And so for everything that we bring in, we can cross out the H minus H ref. And so we can get rid of those conditions. Now, the other piece of information that we're going to know, and we saw this in the last example problem, is the enthalpy of formation for oxygen and for nitrogen is both 0 at the standard condition. So we can get rid of enthalpy of formation for those values right away from our setup. And so we have been able to eliminate a lot of the things that we didn't need. Now, the final thing that I'm going to do is just set ourselves up so we know what we're looking for, and that is we're going to replace all of the enthalpies of the state on the product side with some green enthalpy values here, and that indicates that is what we're going to need to separate out, and that'll be the next step in this problem. And we'll pick that up on Monday, is now trying to set ourselves up to solve for each of the green values, which is the enthalpy at the product state, which will help us get the final temperature of the system, which is the adiabatic flame temperature. Okay, so that is what we'll pick up on Monday. We'll finish up this problem. We'll kind of wrap up combustion on that. Otherwise, that is the end of lecture today. So I hope you guys have a good rest of your day. You enjoy your weekend. But my reminder is make sure that you start on the homework and make sure you start reviewing for the exam. The exam is next week in class or in lab, so do be prepared for that. Otherwise, if you do have any questions, let me know. Otherwise, I hope you guys can enjoy your weekend, and I will see you on Monday. And Paul, looks like I have a question from you.
Yeah, just about